We have covered the difference between emulsions and microemulsions. Now come to these things, the multiple emulsions. Multiple emulsions are complex systems where both oil in water and water in oil emulsions exist simultaneously, which are stabilized by surfactants respectively. Previously, in this point, I told you the wrong things. Uh, I have described these microemulsions as a multi-emulsions that O by W by O. That is wrong things. This is biphasic because one phase is dispersed in another phase, but this is monophasic. Okay. In the previous class, I have told that oil in oil or water in oil in water. That is wrong. That is for the that is for the multi emulsions, not the micro emulsions. Now the multiple emulsions. Multiple emulsions are the complex system where both oil in a water and water in oil emulsions exist simultaneously, which are stabilized by surfactants respectively. Among water in water, W by O by W, and oil in water in oil, O by W by O type emulsions. The first one is much more widely used in many applications. Various factors affect the stability of these emulsions. Wide range of applications in controlled or sustained drug delivery, targeted drug delivery, bioavailability enhancement, and enzyme immobilization are found, and these are promising research areas. In case of multiple emulsions. Multiple emulsions can be employed as an intermediate step in the microencapsulation process, and those are used in oral drug delivery system. So we can expect that a novel carrier system for drugs, cosmetics and pharmaceutical agents is provided with the advancement in techniques for preparation, stabilization, and rheological characterization of multiple emulsions. So, what are the purpose of emulsions and emulsifications? To facilitate the preparation of relatively stable and homogeneous mixture of two immiscible liquid. Number two is permits administration of liquid drug in the form of minute globules rather than in bulk. Number three, administration of distasteful oil by dispensing it in a sweetened flavored aqueous vehicle. And next, reduced particle size of the oil globules may render the oil more digestible and more readily absorbed. For example, increased efficacy of mineral oil as a cathartic when emulsified. These are the theories of emulsification. Okay, first is monomolecular absorption theory, second is oriented wedge theory, third, oriented adsorption theory, next, plastic or interfacial film theory, next, surface tension theory, next is interfacial tension theory, then Fisher's theory or of hydrates and solvents, and finally viscosity theory. So, monomolecular adsorption theory. This is an important theory, monomolecular absorption or film formation. Surfactants adsorb at the oil-water interfaces and forms a monomolecular film. So surfactants adsorb at the oil-water interface and form a monomolecular film. This film rapidly envelops the droplets as soon as they are formed. Agents having higher interfacial activity are better suited for this purpose. The monomolecular film should be compact and strong enough so that it cannot be easily disturbed or broken. Is this understood? That surfactant adsorbs at the oil-water interface and form a monomolecular film to the droplets. This film rapidly envelops the droplets as soon as they are formed. Once they are formed, they rapidly envelope the droplets. Okay. The agents having higher interfacial activity are better suited for this purpose. A monomolecular film, single film, that's why monomolecular film should be compact and strong enough so that it can't be easily disturbed or broken. Here you can see this this total thing is the outer surface of the droplet, and these are the surface active agents. This is the head and this is the tail. See, this is creating a layer, a single layer. That means monomolecular layer. So the monomolecular layer or film that should be so compact. See, so compact and strong enough so that it cannot be easily disturbed or breaked. This film cannot be easily disturbed or breaked. So surface active agents or amphiphils, these are the amphiphils, reduce the interfacial tension because of their adsorption at the water at the oil water interface to form the monomolecular films. These are the examples of this theory. For any reason, if the film is broken, sorry. Uh, in case of monomolecular absorption theory, for any reason, if the film is broken, it should be elastic and flexible enough so that it can be reformed rapidly on moderate agitation. Okay, so what is the thing? If if the film is broken by any chance, so the film should be too much elastic and flexible enough so that once we agitate or shake uh, the system, that means on moderate agitation, the film can be reformed rapidly. The physical, chemical, and mechanical properties of the interfacial films are of importance in stabilizing the emulsions. Attempts have been made to use a combination of surfactants rather than a single one to impart these characteristics to interface. It is assumed It is assumed that they support each other and strengthen the monomolecular film. The surfactant blend consists of a water-soluble and an oil-soluble surfactants. The hydrophilic surfactant approaches the interface from aqueous phase side, while the oil-soluble surfactant approaches from the oil phase side. At the interface, the two surfactants interacts to form a complex and condense as a monomolecular film. The interaction within a mixture of emulsifying agents at the interface and nature of is film is formed. A combination of sodium cetyl sulfate and cholesterol leads to a close packed complex film at the interface. So, the interaction within a mixture of emulsifying agents at a interface and nature of film formed is depicted in this figure, where a combination of sodium cetyl sulfate, that is hydrophilic, and cholesterol, that is lipophilic, leads to a close packed see leads to a close packed complex film at the interface that produced an excellent emulsion. Thus, a blend of surface active agents produce good emulsions. However, it should be stressed that a blend of surfactants may also produce poor quality emulsion if the interaction between them is not stronger at the interface. Sodium cetyl sulfate and oleol alcohol. Sodium cetyl sulfate and oleol alcohol do not form a close packed film, and therefore their combination produces poor emulsion. See, here they are formed closely, very closely packed, sodium cetyl sulfate and the cholesterol, but here not too much closely packed. So they produce a poor emulsion. Cetyl alcohol and sodium oleate produce a close packed film, but complexation is negligible and therefore again produce poor emulsion.